Let's see what their question is. Did you have a question, Amy? Okay, cool. So, just like I said in this chapter, we're going to be talking about the basic statistics. I believe we talk about the sample mean, the population mean, and all that jazz. So you've probably heard of those before. If you haven't, it's not that hard. So, in chapter 3, so far we discussed how to organize, present data by creating frequency distributions and graphs. Now we'll discuss how to summarize data, so using numbers. So, first we will discuss the measures that describe the center of the distribution that are called the measures of central tendency. So, that's like the mean, the median, the mode. So, what's the question? So then we will discuss the measures that determine the spread of the distribution, and those are what we call the measures of variation. So that's like how much variation is there in our data points. So that's the average, like the difference a point is away from the mean. So section 3.1 is all about the measures of central tendency, so that's what we're going to talk about today. Is there any way you could turn down the brightness? The sheet is hard to see. Let me see. Let me do this and see if it works. Does that work? Okay. So, section 3.1 is all about measures of central tendency. So we're going to talk about two different types of measures of central tendency, one for the population and one for the sample. So, recall from chapter 1 that we collect data from either a population or a sample of a population. So, sample is just a subset of the population or a collection of individuals from it. Yeah, we got another question. It's all black. Try this. Is that better, Colton? So, I didn't get a response, so I guess so. So, when measures are obtained by using all of the data values in a specific population, we call this a parameter. So, a parameter is what we want to estimate based on the sample data we get. So, and when measures are obtained by using data values from a sample, we call these statistics. So, a little remark there. So, we use sample statistics to make inferences about population parameters. So that's why we compute these, because these are going to be hard to find. Because, say, for instance, you're taking a sample of individuals at OSU. You don't want to have to talk to whatever it is, 25,000 students we have. You want to take a subset of that because it's going to be easier. And then you can make inferences about the whole population. So, for example, suppose we wish to know the average age of all OSU students. Since there is a large number of students, it might be best to find the average of a sample of students and then make an inference about the entire population. So, therefore, the age, I think it stopped screen sharing. It's just streaming a black screen to me. Can anyone else see the paper if you're online? Colton, I think your screen may just be messed up. So, therefore, the average age of a sample of students would be considered a statistic because it comes from the sample. Oopsies, I spelled statistic wrong. Statistic. And the average age of the whole OSU population would be the parameter. So in this case, The statistic we're looking at is the sample mean. And then in this case, the parameter we're looking at is the population mean. So does anyone know what the mean is? Yep, average. So you just take a bunch of data points, add them up, divide by the total number, and that's your average. So that's what we're going to talk about this chapter. So we're going to look at some formulas for them. So the mean, which can also be called the arithmetic average. Yep. The arithmetic average is calculated by taking the sum of all the data values and then dividing by the total number of data values. So this is just average. So we could also use a couple formulas to calculate this. So the sample mean, which we denote as x bar, so x with a bar on top, is equal to the sum of the xi's over n. So the xi's are just our individual data values. So say we have x1, x2, and we're adding up all the way to xn, and we're dividing by n. So these x1 to xn's are just data values. So xi is a data value. So say if we were measuring height, one of the data values could be 60 inches. So, and then n is the sample size. Okay, so that's how we find the sample mean. We just want to take all the data values, add them up, and divide by the total. That's how you find the mean, or the average. So, what do you think the formula for the population mean would be? Only one thing is going to change in that formula. Well, actually two. So it's still going to be the same formula, except this n right here is going to be capital N for the population size. So the population mean, which we denote as the Greek letter mu, like that, is equal to the same thing, the sum of the xi's over capital N. So this is equal to, again, x1 plus x2 all the way up to xn, divided by uppercase N, or xi are our data values, and capital N is the population size. So let's look at an example. So the data below show the number of patients in a sample of 6 hospitals who acquired an infection while hospitalized. Find the mean. So let's see if y'all can find the mean without my help, and then I'll go over it. Once you figure it out, scream it out. Anyone got it? You say 64.8? That's correct. So what you literally, someone said something. 64.83. Yep, basically right. So what we want to do, so we have a sample, so we're going to get the sample mean, x bar. So that's equal to the sum of the xi's divided by the sample size. So all these xi's right here are our data values. So we're going to add 110 plus 76 plus 29 plus 38 plus 105 plus 31 We're going to divide that by 6. So that ends up being 389 over 6. Which equals, I just rounded to 2 decimal places, so 64.8. So, does everyone think they could use that formula? Plug numbers in, that's it. So, for the second one, it says the mean of a data set of with 4 values is equal to 39.5. If 3 of the data values are 51, 23, and 46, find the 4th data value. So, does anyone know how to do that? So, how it's set up, so we have the mean is equal to 39.50, which equals, so we have the sum of the data values over n. So the sum that we have is 51 plus 23 plus 46 plus our unknown data value, let's call it y. And then we're dividing that by 4, and it equals 39.50. So what you want to do in this case is what? We're going to solve for y by isolating it. So first, you're going to multiply by 4 on both sides. So if you do that, that'll get rid of this 4 and leaves you with that. So, God, I hate when that light turns off. So, what we want to know is what's 4 times 39.5. And if you plug that in your calculator, it's 158. So then we have 158 is equal to 51 plus 23 plus 46 plus our unknown data value, y. So then what we want to do is just solve for y. So we're going to add up these 3 numbers and subtract them to this side, and then we'll just have y. So we have 51 plus 23 plus 46, oops, not 56, 46. That equals 120. So that means that 158 equals y plus 120. And to get rid of the 120, we just subtract it over. That cancels on this side, and that leaves us with 38 equals y. So the 4th data value we need to achieve that sample mean is 38. Does that make sense how I did that? Just using that formula. Okay, is everyone okay with those 2 examples? Pretty simple stuff. So, the next thing we're going to talk about is the median. So the median can also be known as the midpoint. So the number in the middle. So the median, which denoted MD, is the midpoint of the data. Okay. So there are some steps for finding the median. So you could arrange the data values in ascending order. So we just basically put the numbers from lowest to highest. Then we determine the number of data values in the set. So we just count how many values there are. And then we use this rule. If n is odd, the middle value is the median, so the number in the middle. And if n is even, the average of the 2 most middle values is the median. So, an example here. So, it says find the median of the following test scores. So, we have all the test scores here. So, first we want to arrange them in ascending order. So, the lowest is 72. Then it goes to 79. 83, 86, 88, 92, 98, and 99. So now we want to count how many numbers are in our data set. So we have 1, 2, 3, 4, 5, 6, 7, 8. Or did I count that wrong? Did I miss one? 1. Oh, yeah, there's two 86s. Oops. There you go. Now there's 9. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 data values. So n is odd, so we're going to take the middle data value. So what you basically do is go inwards. So these are the two most out data values. Then go N1, N1. I mess up. So here's 86. So start here. These are the two outmost. Then we go N, 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 and here's the middle one, 86. So then the median is equal to 86. So didn't everyone see how I did that? You just trace it all the way down to the middle. I'm going to make this thing turn back on. Why is this thing so touchy today? Why do they make me wear this? Okay, there. So you can also find this value in your calculator if you have an 83 or an 84. So I will show you how to do that real quick. So you're going to go into Stat, Edit. So I still have this from the class that I taught last semester. So we're going to first clear the list, or all of our list. Okay. So what I'm doing here is just taking all of those values that were in those lists and just deleting them. So we're going to go to Stat and then go to Edit. And then we're just going to enter in the data values we have into this first list L1. So we have 72, 79, 83, 86, 86, 88, 92, 98, and 99. So whenever you're putting them in this list, you don't have to put them in ascending order if you're doing it on the calculator. It will automatically do it for you whenever it computes the stuff. So then we're going to go second, quit, so that'll get us out of there. And then we go to Stat, Calculate, and then one variable statistics. So this is going to give us all these statistics we're basically going to use in this class. So you just hit that. You tell what list you want. So whatever list you put the data values in. So I put mine in L1. So I'm going to go second 1, which takes me to L1, and then calculate. So you notice it gives me the sample mean, the sum of all the x's, the sum of all the x's that squared, the standard deviation of x, which we're going to talk about later, the population standard deviation, and the sample size. So that's the minimum value, Q1, we'll talk about that later. But then it says MED, the median, and it's 86. So everyone see how I did that? Easy enough, you can just plug it in the calculator. So now what happens if we add one more value to the data set? So it's the same set except we add a 99. So then it's going to be 72, 79, 83, 86, 86, 88, 92, 98, and 99. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I missed another one, 99. So there we go. Now we have 10 data values, so n is even. So we need to average the two most middle values. So if we go n, so we have this, 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 and these are the two most middle ones. So we want to take the average of those two. So we have the median is equal to 86 plus 88 divided by 2, which equals 87. Did everyone see how I did that? So you just trace it into the middle to see which two most middle values you have. So you could also do it in the calculator. So what you could do is go back into stat edit. So you already have all those values in the calculator. All you're doing is adding an extra 99. So just type in 99. Do the same exact thing we did. Stat, calculate, one variable statistics, calculate, and it says the median is equal to 87. Did that make sense? Did y'all get lost? Okay, cool. So that's how you find the median. So it's just the number in the middle. So the mode is what? Does anyone know what it is? Yep. So the mode is the value that occurs most often in the data set. So a data set that has one number that has the highest frequency is called, what do you think? Remember how we had a distribution that was bimodal? So if it's just one mode, what do you think it'd be called? Unimodal. Okay, so if there are two values that occur with the same greatest frequency, so the frequency is the same, but you have two of them, so both values are considered to be the mode, and the data set is called what? I just told you all that answer a second ago. Yeah, bimodal. So if a data set has more than two modes, then the data set is called, you probably won't know this one, multimodal. So multi, because it has multiple modes. So if all data values have the same frequency, then we say there is no mode. A little note, do not say that the mode is 0. And why do you think that is? It means you have, well, the reason why is, I don't know how to say it like properly, but 0 may be a value in the data set. So say if you're talking like Kelvin or something like that, you could have a 0 Kelvin temperature, I think. Don't know, I'm not a chemistry person. Or if you're talking Celsius, you could. Does that make sense? So say we're having a data set of temperature that has degrees in Fahrenheit. So you could go from, say we have like negative 12 to 0, 12, and 14. So all of those data values occur the same number of times in the data set. And 0 is actually a value. So we couldn't say the mode is 0, that there's 0 mode, because 0 could be a data value. I confused myself even saying that. So if we said that the set had 0 mode and 0 was actually in it, and it was occurring the same number of times that every other number was occurring, that would be wrong. Does everyone follow that logic? Cool. Why is this microphone so freaking touchy today? Can I turn it down? I don't know. Okay, so let's look at two test score data sets that we had before and find the mode for each of them. So we're just going to look for the number that occurs the most often. So in the first data set, 99 occurs once, 72 occurs once, 98 occurs once, 88 occurs once, 83 occurs once, 79 occurs once, 92 occurs once, but 86 is in there twice. So the mode would be 86. Makes sense? There's an 86 there and an 86 there. The mode equals 86, so this data set is unimodal. So does everyone understand why 86 is the mode there? So the number that occurs most often. So every number in here occurs once, except 86, it occurs twice, so it's the mode. Okay, so the next one we have in this data set, so 86 is still going to be one of the modes because it occurs twice, but we also added another 99, so 86 occurs twice and 99 occurs twice, so we have two modes in this case. So the modes would be equal to 86 and 99, and this data set would be what? Bimodal, so that's two modes. Everyone okay with that? Easy stuff. So the next thing we could talk about, that's another measure of central tendency, is the mid-range. So the mid-range is a rough estimate of the middle. So where have we seen this before? So the mid-range we're going to do by taking the highest value, adding the lowest value, and dividing by 2. So where did we see this specifically last week? We used it on a frequency polygon. Remember how we talked about class midpoint? We took the lowest limit plus the highest limit divided by 2. So that's where we've seen it before. So the class midpoint in chapter 2. So does that make sense to everyone? Does everyone remember that? Okay. Everyone online, you following what I'm putting down? Good talk, good talk. So find the mid-range of the following data set. So we want to take the lowest value plus the highest value and divide by 2. Colton saying something. Cool beans. So I'm just going to say MR for mid-range, like we say, like the little abbreviation. So we want to take the highest value in our data set, so that will be 23. And then we want to add the lowest value in our data set, which will be 5. And then we divide by 2. So what's 23 plus 5? 28 divided by 2, 14. So a rough estimate of the middle for this data set would be 14. Everyone follow that logic there. So what are we going to talk about next? So the next thing we're going to talk about is the weighted mean. So this is how actually some classes find your grades, depending on the way professors do grades. So the weighted mean is the mean of the data set in which not all values are equally represented. So they all don't have the same weight. So we can calculate the weighted mean by multiplying each data value by its corresponding weight and dividing by the sum of the weights. So usually in this class, the total weight will equal 100% for 1. So what we want to do is first give the formula. So x bar, the weighted mean, is equal to the sum of the w times x over the sum of the w's. So where W is equal to the weight, and X is equal to the data values. So, an example to illustrate this will make it a little bit easier. So, a statistics class has the following rating rubric. A student's corresponding scores are on the right, find the weighted mean. So, what we want to do is take each of these weights, multiply it by the data value that goes along with it, and then sum them up, and then divide that sum by the sum of the weights. So, in this case, we have X bar. Okay, so what I'm going to do, since this is a percentage, I'm going to turn it into a decimal. So how do I turn 10% into a decimal? Move it over twice. Yeah, close enough. So take it over 1, 2, so it's 0.1. So then we have 0.1 times what? Be 0.1 times 95. So the weight of that times its data value. So you could also say the 10%, and you could take 10 times 95. But whenever you take the total sum of the weights, you'll end up with 100 and not 1. So you're just doing 100% instead of 100%, which is 1. Basically the same thing. You'll get the same answer. So we have 0.1 times 95, which will take care of this first one. Then we add the weight times the data value. So in this case, the weight of the quizzes is 20%, and they got an 89 on the quizzes. So that would be 0.2 times 89. So then on this one, so we have 3 exams, each is worth 15%. So we're going to take each of these exams and multiply it by the 15%, and then sum those up. Does that make sense? Just using this formula here. So what it's going to look like is, so we have 0.15 times 92 plus 0.15 times 79 plus 0.15 times 86. So does that make sense to everyone? So I just took the 15% that each exam is worth, and then I multiplied it by the corresponding score for that exam. Is everyone following how I'm doing it so far? Okay. So then what would I add for the last term? What do you think it would be? Let's see if anyone's getting what I'm doing. What was that? Yeah, 0.25 times 90. So then all of these here are, in this formula, the sum of the W's times X's. So now we need to divide this total by the sum of the weights. So divide. So let's take the weights. So we have 0.1 plus 0.2 plus 0.45 plus 0.25. So that's 0.3 plus 0.7, which is 1. So all you're going to do is just take this right here and add it all up and tell me what you get. Everyone online, do you get what I'm doing here? This is basically how you calculate your grade in a class that has different weights on like homework and quizzes and stuff like that. Did anyone figure it out? Correct. So in this class, if you got an 88.35, what do you think I would give you for the course? An A? Did someone say that? You'd probably get an A. I'm pretty generous with the way I grade. Last semester, since we had COVID going on, we had to drop our grading scale. And anything above an 85 was an A. I don't know how generous I'll be this semester. But it'll probably be around an 87. Golly. Okay, so is everyone okay with that weighted mean example? Okay, so if you want to calculate your grade in some class, that's how you do it. If there's unequal weight on everything. So now what we want to talk about are a couple different types of shapes. So recall the three distribution shapes we talked about in chapter 2. So we had a symmetric distribution, a right skewed distribution, and a left skewed distribution. So when the data is skewed, the mean gets pulled to the tail of the distribution. So it depends on which way it is skewed, which way the mean is going to get pulled. So if my distribution is right skewed, the mean is going to get pulled more towards that tail. And then if it's left skewed, it's going to get pulled more towards that tail. So you may need to know that. That was on the final exam last year, and barely anyone got it right. So I was nice enough and gave them all points for it because the final exam average was like a 60%. So this semester, it's going to be multiple choice, so I don't have to grade it. So we'll make it easy. So, which means most of the data value is represented in the hump. So the hump of the thing. So in the case that the distribution, that the median, okay, in this case, the median is more appropriate to measure the central tendency because we're having the clump of data values like actually more near the median than we are the mean because the mean is getting pulled towards the tail. Does that make sense? Did everyone get that? So I'll draw a picture. So say we have something that is right skewed like that. So if it's right skewed, the mean is going to be like more towards here. Be the mean. Whereas the median, the number in the middle, will probably be around here. So this is going to be a more accurate approximation to a measure of central tendency because the median is kind of more where the clump of data is. Oops, can't see that. So there's the mean, so it's getting pulled towards the right because it's right skewed. And here's the median. So notice that the clump of data values occur like right around here. So this is a rough approximation of the median or the center. So that's a little better approximation than this mean, which is pulled down here where it's kind of closer to the tail. Does that make sense? Okay. Similarly, for the left one, it's going to get pulled more towards this way, and the median will be up at the top. And again, it is a better measure of the center. Okay. That kind of makes it a little bit easier. Oh, I literally had graphs on the next page. So I'll just show you anyway. Okay, so this first one is going to be right skewed. So we're going to draw something that looks right skewed. So in this case, our distribution is right skewed, so the mean is going to get pulled more towards the right. So we say the mean is about right here. So, and then, so that means the median, which is the middle, is going to be roughly around here. And obviously this has the greatest frequency, so this is the mode. So that's what it'll look like if it's right skewed. Sorry, someone's asking a question. Did any of y'all have any questions about what we're doing? What's up? What's up? I mean, that's just a rough estimate of the mode. So say we have like a distribution, like say you have a dot plots, for example, and you have like the highest bar right there. So that's the mean, the mode, and then below that'll be like the median and the mean. Does that make any sense? So if you have a distribution, say that's like, so here's the rough curve that goes with that. So we can obviously see that the mode is going to be somewhere around here. So it's going to be somewhere in this bar. And then the median, the number in the middle. So you see that these numbers are pretty spread out. So the number in the middle is going to be a little bit towards like right here below the mode. And then since the mean gets pulled down towards the tail, then the mean's there, roughly around there. Does that make sense? Okay. So the right skewed graph seems to have the most of the bulk of the data to the left. That's where my confusion is. So Colton, right skewed means there's barely any data values on this left side. So whenever I have such a high value, say I have values 11, 12, 16, 20, and 40. So if I want to find the mean of this data set, I just add those all up. So that's 11 plus 12, that's 23, plus 16 is 39, plus 20, 59, plus 40 is 99. So the mean would be 99 over 4. Wait, is the right-hand side of the graph the left side? The right-hand side of this graph right here is where we have the higher data values. So for instance, it would be like where this 40 is. So in that case, the sample mean would be 99 over 4 is 24.75. So do you think 24.75 is actually the mean? No, we have most of the data values are occurring within 12 to 20 or 11 to 20. So we'd expect the mean to be in that range, not on that high end. So in that case, we'd take the median to be the accurate representation. So it'd be 16. Does that make sense? Because it's more in the middle than 24.75. That's what it means. Well, we have study guides for exams. There actually is an old exam on Canvas right now, like what you will see next, or whenever the exam is. So I'll show you it real quick. This. Did anyone actually see the old exam I posted? Okay, so share this application window over here. So, Catherine, to answer your question, there actually is an old exam that I gave last fall to my students. It will be your exam this semester will be pretty similar since we have about the same amount of time to complete it. So this is basically your study guide. So right now, all that we've gone up to is this right here. So you should be able to understand most of the exam up to question 3 of the free response. I actually put the key there too, so if you want to like work out the exam on your own and then check your answers, you're more than welcome to. So the exam is a little long because we have a little bit longer too. Take it, and there was my bonus question last year. What time are my office hours? So I could ask something like that, or I could ask, where is my office at? So usually I'll put something on there like that. So as you can tell, next chapter, we're going to talk about probability. So you're going to need to know probability because it's about 2 or 3 questions on your exam. And it ends up being worth, let's see, what is that? 14, 12, 10, 36 points. That's how it's going to go. So that'll be your study guide, and I will also go over it in class. That way you understand how to go through it. Is everyone okay with that? I may steal another instructor's practice exam too to look over, because I may steal some questions from theirs as well. That's what I did last semester. So, since we have this right skewed one here, we could have a left skewed one. Oops, those bars should have been longer. There, in this case, the curve that goes over it would be somewhat like that. So you can tell that there's not as much data on the left-hand side, so we're going to get the mean pulled to the left-hand side. So it'll be around, say, here, I guess. The median, the number in the middle, will be roughly around there, and the mode's going to be somewhere in here. So just because I draw this and I say the median is right here in this bar, that doesn't mean it's going to be inside the bar. It's just going to be roughly in that location on the distribution. Does that make sense? Okay. So when the data is symmetric, that means it's evenly spread about the center, or roughly evenly spread. Then the mean, the median, and the mode could all be used as a measure of central tendency. So a symmetric distribution looks like this. Oops, close enough. So then if I draw a curve over it, right here in the center, or roughly in the center, is going to be the mean, the median, and the mode. So they're all going to be pretty much the same. Okay, so is everyone okay with those? It's a little confusing, but it makes sense if you think about it. Okay, so do y'all want to talk about the properties and uses of central tendency, or do you want me to leave that to you? Because I think I left it to the students last semester, to be honest, because it's long. So I'll talk about a couple of each of the properties. There we go. That'll make sense. That way you know a little bit about it. So the mean. So the mean is found by using all the data values. So that's obvious. We're taking all the data values and dividing by the total number of them to find the mean. So we use the mean in computing other statistics, such as the variance. So that's what we're going to talk about in section 3.2, is the measures of variation. So we have the variance and the standard deviation. You could also have something called the interquartile range. So, see, the mean is affected by extremely high or low values, which we can call outliers. And whenever we create box plots later, you will see how to identify outliers and how you can tell whether something is an outlier or not. An outlier just means it's crazy high or crazy low compared to all the other data values. So if we have those extremely high or extremely low values, it may not be the appropriate average, the mean won't, to use in the situations. That's just how we had up here. We had it skewed, so whenever it's skewed, it gets pulled more towards the tail. So then it's not an accurate representation of the actual mean, of the actual measure of central tendency in the middle. Does that make sense? I think I'm losing about half of you in here right now. So, is everyone okay with that? Okay. So, the median is used to find the center, the middle of the data set. Just how we showed earlier, we're going to find the middle value, and that's basically the median. So, that's what it's used for. The median is affected less by the mean, by extremely high or low outliers. It just matters how many data values are in your set. It's not really going to affect the median. It just matters how many you have. That way, it's the number in the middle or the average of the two in the middle. So the mode is used when the most typical case is desired. I don't know what that means. Don't worry about that. So the mode is easiest. Average can compute because you just look at the data set. What's the number that occurs most often? That's the mode. So that's one of your measures of central tendency. We don't use it very often unless the distribution is symmetric. In that case, it equals the mean and the median. Oh, also, the mode is not always unique. As you've seen in one of the examples, we could have two modes. With that test score example, we had a mode of 86 and 99. So the mode is not always unique. So the mid-range is easy to compute. It gives a rough estimation of a midpoint, and it is affected by extremely high or low values because we're adding the lowest value to the highest value and dividing by 2. So if I have high values, it's going to affect that mid-range compared to if I don't. Does that make sense? Say, for instance, if I have a data value of 11 and the highest one I have is 89, then the midpoint will be 50, so it's 11 plus 89 divided by 2. But if I have a highest point of like 62, then the mid-range will equal to 11 plus 62 over 2, which is equal to 73 over 2, which is 36.5. And there's quite a bit of difference there. So that's how it's affected by extremely high or low values. Did that make sense? At all? If it didn't, you can ask me. So, is everyone okay with the mean, the median, and the mode? Okay, neat. So, next thing I'm going to talk about are measures of variation. Okay, so it is not enough to describe a data set just using the measures of central tendency, so the mean, the median, and the mode. We also need to describe the variability, which is also known as the spread of the data. So we can have many situations where the mean is the same, but the variability is different. So say, for instance, I have a graph here of y versus the relative frequency. So the relative frequency is just, remember, it is the frequency of one point or a class over the total frequency. So this is just a rough shape based on some distribution. So notice here that the mean is always the same in these three, but there's a lot more spread of data values here than there is here. Does that make sense? So that means this distribution here is going to have more variance or more spread about the mean compared to this one. Can everyone understand why that is? Okay. Because you'll understand why in a second when I give you the formula for the variance as to why this one would have a higher variance than this one. So we will go through some ways to measure the variability. So the one you've probably seen before is the range. We talked about it in chapter 2. So does everyone remember how to find the range? Take the highest number, subtract the lowest number. That's the range. So the range is the difference between the largest and the smallest number in the data set. So R, which is the range, is equal to the highest value minus the lowest value. So if you have, say, for instance, some numbers on a line like this, then this distance right there would be the range. Everyone okay with that? That's the highest number, that's the lowest number. So that's the range. So the range shows us the spread of the data, but what happens when there is an extremely high or extremely low data set? So, or data value, I mean. So let's look at an example. And then you can tell me what it is based on that. So say for instance, I have these 3 points right here, and then I have some way down here. So how is this going to affect the range if I have an extremely high data point compared to the others? That range is going to get larger because I'm taking this gigantic number and I'm subtracting off these of the lowest one. So the range will get bigger. So that means the range becomes larger and doesn't accurately measure the spread. Because there is little variability here and here, but over the whole interval, there's a lot of variability because there's a big gap here. Does that make sense? So say, for instance, in this example up here, so I have all these points. So that was my range for just this case when I had these 5 points. But if I add a point out here, then that range is going to increase drastically compared to what it was before. So in this case, we need a more meaningful statistic to measure the spread, and that's what we're going to talk about. It is also known as the variance. So the variance is the average of the squares of the distance each value is from the mean. So basically, this means the variance measures the average degree to which each point differs from the mean. So, therefore, the higher the variance, the larger the overall range, and vice versa. Okay, so does everyone understand why this is? Because the variance is the degree to which each point differs from the mean. So if I have points that are out here compared to here, so the mean's going to be around here somewhere since there's more data points on this side. Oh, gosh dang it. So the mean is going to be roughly over here because there's more data points on this side, I guess, or it'd be kind of over here. So then how much it differs from the mean, if the mean is over here, then I'm taking this difference here and then squaring it and adding them up. So that's going to be quite large compared to if I had the mean is right here and all my data points are right here. So then if this happens, these data points are closer to the mean. So whenever I take the difference and square it and add them up, it's going to be a lot smaller than with these data points. Does that make sense? Okay. So then let's define the formula. So the population variance, sigma squared, is equal to the sum of the xi's minus mu squared over n. So where xi is each data value, mu is the population mean, and n is the population size. Okay, so does that make sense to everyone how this says right here? So the variance is the average of the squares of each distance the data value is from the mean. So what is it doing here? It's taking each data value we have, subtracting off the mean, and then squaring it. So that's telling us the distance squared, so the average of the squares. So we're squaring these distances, and then we're going to take the average of all of them once we sum them up. So we're dividing by the total. Does that make sense? Does everyone get why I'm doing that? So then the sample variance, which is s squared, is equal to the sum of the xi's minus the sample mean x bar squared over n minus 1. Okay, I will tell you why the n minus 1 is there in a second. Colton, what was that about? I wasn't paying attention. I don't understand the formula. This one right here? Okay, so the variance here, so the variance is the average of the squares, so the average of the squared terms of each distance each data value is from the mean. So what we're doing, we're taking each data value we have, we're subtracting off the mean, so that'll tell us the distance between each data value and the mean, and we're taking the average of the squares. So squares means we want to square this term. We want to add up all those squares and then divide by n to find the average. Does that make sense, Colt? Okay, cool. So in this case, we have an n minus 1 in the denominator. So here we have xi is equal to the data values that we are plugging in. X bar is what? Sample mean. And n is the sample size. So why are these formulas different? You don't really need to know this, but we'll write it down anyway. So since samples are usually smaller than the population, we divide by n minus 1 to give a slightly larger variant or slightly larger value, since dividing by n sample size underestimates the variance. I don't know if you will need that for the homework. It's just always been in the notes, so I put it in there. So you won't really see that on the exam. So I just put that in there as a note. So whenever we come to chapter 7, this n minus 1 will come in handy because it's going to be known as the degrees of freedom. So that's what we're going to use when we create confidence intervals. So to illustrate what we just talked about, let's do an example. So assume the data below is given from a population. Find the variance. So remember the variance, or the population variance, sigma squared is equal to the sum of xi minus mu squared over n. So what we want to find is mu. So mu is equal to the sum of the xi's over n, where n is the population size. So we said this data right here is from a population, so the population will just be 1, 2, 3, 4, 5. So n is 5. So then we're just going to add up all these values and divide by 5. So that will be 2 plus 4 plus 5, so that's 11, 19, 22. 22 over 5, which equals 4.4. So, is everyone okay with how I got that? So, now we're going to find the variance. So, it is equal to the sum of the xi minus mu squareds. So I'm going to take each data value, subtract off the mean, and square it. So that would look like 2 minus 4.4, that quantity squared, plus 4 minus 4.4, that quantity squared, plus 5 minus 4.4, that quantity squared, plus 8 minus 4.4, that quantity squared, plus finally 3 minus 4.4, that quantity squared. All of that over what? 5. Over n, which is 5. So, someone tell me what you get. I'm making y'all work it out, that way you know how to do it. Colton, are you getting what I'm doing? Cool. Anyone got an answer? Okay. So if you add all of them up in the numerator, you get 21.2 over the denominator 5. So it's 4.24. Okay, is everyone okay with how I did that? You take the difference. Each of these data points is away from the mean. You square them. You square those distances. Then you add them all up. And then since you want to find the average of all those square distances, you divide by the sample size or the population size. So now we assume the data is from a sample and find the variance. So remember that s squared is equal to xi minus x bar. at quantity squared over n minus 1. This should be a sum. Okay. So the sample mean is going to be equal to the population mean because the sample size is still the same as before, and we still have the same data values. So I'd still have 2 plus 4 plus 5 plus 8 plus 3 over 5, which is the same thing as up here, so that's 4.4. And then I'm taking each data value, subtracting off 4.4 and squaring, and then adding them all up. So I'm still going to get the same numerator as I did up here, but the denominator will be the same. Will be different. So we'd have 21.2. What would be our new denominator? What's n in this case? What's the sample size? 5. So take 5 minus 1, n minus 1 is 4. So then the sample variance would be 5.3. Does that make sense? How I did that? Okay. So the next thing we'll talk about is the standard deviation. We'll talk about that next time. The standard deviation is just the square root of the variance. So we'll talk about that next time. Your homework is due on whatever day I said it due. I think it's Saturday. So see you all Thursday. If you all have any questions, let me know.